That's a good question. I gave you guys questions to work through. I was hoping that people would, I try to keep it light. So just a couple of questions in each section that aren't super computational. So I was going to make it due on either on Friday or like on the Monday of the final or something like that. I mean, I guess the point is that those questions cover important ideas. And I know everyone out there has the solutions manual. I was hoping people would use it, that they try the questions, but I was going to pick it up either on Friday or on Monday if people want to get credit for the fact that, you know, they've been working on that stuff, if that makes sense. I guess I should make a note to myself to add that to Canvas announcement. So add Canvas. I mean, the alternative is I can make it optional, but I think a lot of people like to get credit for the work they do, and I think they should if they want it. So if anybody has strong feelings about that, I'm open to listening. It's hard.
Will the final exam still be in person?
Well, I'm coming back on, I should be back tomorrow, or not tomorrow, but Thursday afternoon. So I'll be in person on Thursday. This is not like I'm not gone forever or anything like that. Now, the exams for sure are going to be in person. Even if I got sick with COVID or somebody else does, like the exams basically have to run in person unless there's medical exceptions. I actually had a conversation with the chair about this, about some students that were worried about what would happen if they got sick or, and I was told basically by department policy that math finals must run in person. I mean, there's other ways around it, I think, where it's possible. I think that you can get, like, there's records in the past of people doing something like filing with the DRC if they have major medical emergencies and then having things proctored locally through another DRC. But like, if people can avoid that, they probably should, because that's an enormous, like if you weren't in town or you had to go back home because you missed the finals or whatever like that, it basically has to be done by the time the final's over, or I have to give it incomplete.
When is the final? Sorry.
So the final is for this class is scheduled on Monday at 4:30, I believe, is what the final time for this. So there's like basically like that's the worst possible configuration for office hours, because this class is so full of content that I have to teach all through the week. I'm going to have a big office hour on Friday so people can come by. I'm going to post some review stuff tonight. And then, you know, hopefully on Friday, I'm actively considering like running a weekend office hour, which I don't like, which nobody is obligated to come to, but it would be nice to have the opportunity for people to drop in either in person or on a computer and hang out and get questions answered. I would understand if people don't want to come in person because apparently now COVID is just ripping through campus. I think last week, something like a quarter to a third of the math professors were out. I'm getting notifications, like possible exposure notifications in my own stuff constantly.
Is classes going to be in person tomorrow?
Class is not in person tomorrow. Class is also virtual tomorrow as well. Thursday, though, I will be back in person. Although I'll tell you that the content that I'm covering Thursday is going to be virtual. So everything is going to be, everything I'm covering this week by tonight will be up on YouTube. If people are concerned about, you know, attending class or have other things going on, and they don't want to sit in on my live lectures. I'm not saying that people don't like to come to class, but you know, if you have other things going on.
Do you know when the midterms will be graded?
Those are, I'm hoping those are going to be done. I mean, I'll have those for you on Thursday. I will hand them back on Thursday. That's mostly just like sitting down and grinding out the last couple of questions and getting them punched out. And then part of that also is getting the solution guides together. whoever it was that decided that math tests were the best way to evaluate math students is a crazy person. I didn't do it. It's not my fault. I just have to follow the rules.
What would you do then if you had your choice?
If I had the time, I would give nothing but oral examinations. I would have people come into my office and talk to me about what's happening in the class. I wouldn't make people grind out, you know, in a 50-minute period, 6 questions or 5 questions or something like that. I'd have people come in, and I learn a lot more about people, what people know and don't know by talking to them. It also keeps examinations away from grueling computations, which are also something I think oftentimes doesn't reveal what people know and what they don't know. You know, the other possibility is to not run timed exams, but that's also quite difficult, because if you don't run timed exams, then you're doing take-home exams, and that, like, there's an entire world of people that think that the incentives for, I'm not going to say academic dishonesty, but the incentives for consulting outside sources are pretty high if there's nobody proctoring an exam. So it just, this is really why I think the ideal is oral. I've run oral exams for upper division classes before, but it takes a long time. You know, for you guys, it's all short, you know, 20, 30 minutes come in and chat with me. But if I have to do that for 30 students, that's like half a week worth of work just talking about examinations. So I guess the other possibility would be to do, like, in the future, would be to do, like, sort of in-class group examinations, but that runs into the same kind of problems where, you know, you get these really unfair allocations of work, I think, oftentimes in setups like that. So I don't know. I'm not a huge fan of it. There's probably better solutions. I don't know what to do about that, especially in a class like this, which is kind of an ill-fitting, it's computational, but also theoretical at the same time. Okay, so I guess we should get started. Thanks, guys, for I guess whoever's watching the YouTube video later. I hope they appreciate, like, our 5-minute conversation I've just recorded. Yeah, so thanks for dropping in, those people that are here. My intention today and over the next couple of days is to talk about what I think are the real heart of the point of this entire class. And I think in the future, we're going to look to trying to design this class so we can spend a lot more time talking about what we're doing right now. The ideas that we're going to talk about this week were basically associated with the invention of contemporary physics and contemporary mechanics and contemporary mathematical engineering and contemporary applied math. They point the way to a couple of different really interesting areas of study. So differential equations, partial differential equations, differential geometry, differential topology, you know, the study of electromagnetism and the field equations, the study of light. And so these are incredibly important. And so we're going to be talking about chapters 7.1 and 7.2 and 7.3. And I have to warn you that it's going to be very difficult for me. It's not warn, maybe I'm trying to assuage you. We're going to be talking about some theorems that involve integrals, where the integrals are basically, like, really, really long. And the point of this is not to make you grind out enormous integrals. The point of showing you the Stokes theorem and the divergence theorem is so that you start getting a feel for the way that the mechanics of vector calculus tell us things that we can work with theoretically or from an abstract setting that aren't necessarily about you sitting down and doing a triple integral. So the conversation we're going to have about this might seem a little abstract, but that's on purpose because I'm trying to keep the focus on the reason why we're doing this stuff and not on an integral that a computer can calculate, right? There's steps in here that are human steps, but the computation of the actual integrals oftentimes is numerical. So last week, we talked about a theorem called Green's theorem. And what Green's theorem said was it gave us a way of relating these sort of circulation integrals to, or sort of boundary integrals to interior integrals, right? So let me actually look up what Colley's, before I just, like, write something down in a notation that you guys don't know. I'm gonna look up Colley's version of this real quick. So Colley's version of Green's theorem says the following, that for a sufficiently nice surface, that the integral around the boundary of this differential form was equal to the double integral over the interior of the region of this exactness condition. My dm dy dx dy. And the idea of Green's theorem is it gave us a way, remember that this is actually equal to the integral around the boundary of f dot ds. Okay. So the idea here is we had some domain D, and we parameterized the boundary of the domain. So that's the boundary of the domain. And it gave us a way of one way of interpreting that one version of interpreting this was it gave us a way of connecting vector fields flowing through a disk versus vector fields are like circulating around a boundary. Or probably more precisely here, this is a double integral over the interior of D. And this is a single integral around the boundary of D. And the idea that we can take the interaction of a vector field and a curve, or a vector field in a set, and move back and forth between one-dimensional versions on the boundary and two-dimensional versions on the interior underlies possibly the most important theorem in vector calculus, which is called the Stokes theorem. To get that, we're going to have to talk about parametrized surfaces. And so the first part of our understanding of this is going to be to talk about what it means to parameterize a surface. And we're going to do this in the same way that we parameterized curves with paths. So the idea is what we want to look at. So we want sort of Green's theorem, a version of Green's theorem in R3. This is kind of what we're after. We can't do that unless we have an object we can do it with. So previously we've parameterized curves. Our first goal is going to be to talk about parameterized surfaces. And of course, there'll be videos that have, I've already recorded videos on 7.1 and 7.2 that are up, I sort of did in preparation for this. So I encourage you to look at those as well. So with the parameterized curve, what we did is we said, okay, so you had some path, and the path was a function x of t. And what x of t did was it took some interval I from a to b, and it stuck it into, say, R3. And what you got out of that was some kind of curvy shape in R3. So, kind of moving around, doing stuff. And this is, say, x of a, and this is x of b. And it gave us a notion of traveling down the path. So what the x did, so the x was called the path. And what the x is, it carved out the curve as we travel through space. And we did some things with this. We calculated the Frenet frame with this. We noticed that there was a notion here that, like, really what's going on with the parameterized path is I can study the motion of a particle traveling that path by looking at the derivative of the path. If I took the derivative of the path, I end up saying something about the motion of the particle. And we did a lot of work with x prime of t. We developed quantities called ds and vector ds that involved x prime of t, where ds was equal to the length of x prime of t dt. That gave us a way of chopping the curve up into little pieces called ds. And then we had the vector version of it, ds, which was x prime of t dt. And that gave us a way of figuring out how a vector field interacted with the path. And so we're going to take this basic idea and lift it up to be about surfaces in R3 instead of curves in R3. So we're going to try to generalize this idea. Okay, so we got to put some conditions on things here. I'm going to state these once. So we'll let D be a connected open set. The idea here is that I want a surface to just be one object floating in space and not have pieces all over the place. So D is a connected open set plus possibly the boundary. Of D. And we want D to be a subset of R2, which means that I want D to be a collection of points S and T. So I'm going to be parameterizing a two-dimensional thing. So I need two parameters to work with instead of the one parameter we worked with in the path case. A parametrized surface S is a continuous function X that takes D in R2 to R3. And yes, this is specific to two-dimensional things sitting inside of R3. There's generalizations of this to hypersurfaces that you guys can look at if you really like differential geometry. That is 1-to-1, except possibly at the boundary. And that's it. X of D, which is equal to S, is called surface parameterized by X. And I'm going to try to make it more clear with some pictures, kind of what's going on here. So the basic idea is that you have some set in R2, which you call D. And sitting inside that set are points that we think of as being S comma T. And then just as with the parametrized path, we took the interval and we mapped it into some coily thing sitting in R3. Now, if I apply a map X that takes D and turns it into a surface, what comes out the other side is a collection of points. Remember, it's a collection of points in 3 space. This is not a Z equals F of X, Y thing. This is a collection of points where an S and a T go in, and an X of ST, a Y of ST, and a Z of ST come out the other side. So we have some surface sitting inside of R3, where perhaps this point right here is the image of ST. So every point in the domain gets carried over into a point in the surface. Okay. So as an example, here's kind of a cute one. I guess it's too early for me to be using the word cute, right? So if you have D, which consists of the interval from 0 to 2 pi, cross the interval from 0 to pi. When I say cross here, what I want you to think is that these are where the parameter S lives and these are where the parameter T lives. It's the Cartesian product. It's giving us a way of identifying points in R2. And we're going to let our map X be equal to X of ST is equal to A cosine S cosine T. This is the closest I'm going to get to spherical coordinates in the class here. Cosine T, Z of ST is A cosine T. And if you think about what that does for a second, and you know anything about three-dimensional geometry, this is the spherical change of coordinates map. So what this is doing is this is a map X that takes this rectangle that looks like this. There's 2 pi. This is the S axis, and here's the T axis. That's pi. And what it turns it into, that's where I get to practice my three-dimensional drawing skills here, I guess. Okay, so what comes out here? Let's actually just keep track of what happens to one curve first. So let's look at this curve right here. So this curve is the curve corresponding to S is equal to 0. And if S is equal to 0, then X of 0t is equal to A cosine T. Y of 0t is equal to 0. Z of 0t is equal to, oh, this is supposed to be a sine T. There we go. That's better. Z of 0t is equal to A times the sine of T. And those are the equations for, so remember T runs from the interval from 0 to pi. So this is a half circle of radius A. It's a half circle of radius A where all of the y coordinates are equal to 0, which means this point right here is the point 0. Sorry, it's cosine of 0. What does that turn out to be? Oh, no. And I can't undo it. It's lovely. Okay, so if you put in t equals 0, what do you get out? If you put in t equals 0 into this thing, then you get x is equal to a, y is equal to 0, and z is equal to 0, which means you're at this point right here. A, 0, 0. That happens when t is equal to 0. If you put in t is equal to pi, you get out the point minus a, 0, 0, which is back over here. If you put in the point t is equal to pi over 2, then you get 0, 0, a, which is right here. This is minus a, 0, 0. This is 0, 0, pi over 2. And if you think about it for a second, what this tells you is that there's a half circle that's kind of running back like this. It starts at this point and runs this way. So the image of the line that we started with starts at this point in the front and sweeps back to the back, assuming I've calculated this correctly. And if you look at the rest of the map, essentially, don't laugh, because you're going to laugh at the sphere that I'm going to draw right now. You guys try to do this. This is not easy to draw in 3 dimensions. Okay, so there's a piece that looks like this, and then this part comes down like this, and then there's kind of this back here, and this comes over here, and I guess this part connects like this, and this part's right here, and then the sphere goes down. That's actually pretty good. All right, I'm proud of that. So this is the image. So when we talk about a parametrized surface, this is precisely what we mean. We have a map X that turned this rectangular domain that sort of corresponds to an interval, into this 3-dimensional surface, and not with functional notation. Remember, this is not a z equals f of x and y thing. This is a map that carried a 2-dimensional domain into a 3-dimensional set of points. Okay. And so this is an example of what we mean by a parametrized surface. Okay, now there's something I was trying to indicate here when I calculated what was happening to this line right here, which is every line that you draw through the domain ends up mapping to a line of some kind in the surface that you've parameterized, right? If a line goes in, some kind of curve comes out. So those curves, this is an example of something called a coordinate, sorry, not this part. This is this pink line right here that was the image of this pink line is an example of something called a coordinate curve. And so coordinate curves are what we're going to use to define tangent planes in this setting. In the same way we used x prime of t in the curve case to figure out what the tangent line approximation for a curve was, a parametrized curve, we're going to have to come up with some way of computing tangent lines here, or tangent vectors here. And the way we're going to do it is exactly this. We're going to draw lines in the domain, and we're going to take the derivatives of the images of those, and those will give us vectors in the range. So I'll make that more clear, not with the definition, which I'll write first, but with the picture that comes second. So let's let S be a surface parameterized by X. And let's suppose X takes D in R2 into R3. If we freeze one of the variables, if we freeze T to be some fixed value T naught, then we get a map. In fact, we get a path where every S value gets sent to this thing, X of S and T naught. That's going to turn out to be a path in R3. And if we freeze S is equal to S naught, we get a different path where each T value gets sent to X of S naught, comma, T. And these paths are called the coordinate curves at S naught, T naught. And it's much easier to understand from a picture what's going on here, I think, than it is just from the definition. So again, I'm doing my best with these pictures. Imagine you have some domain D, and X takes D and it turns it into some surface. So let's suppose we got some surface floating around over here, some kind of squiggly dude. Then if I take a point in the domain over here, if I take a point S naught, T naught, and I compute the coordinate curves through that point, Well, if I hold a T naught value, so say T is equal to T naught, and I go through the point here, and I look at the image of that blue curve, well, I already know that the S naught T naught is going to get mapped to some point over here called X of S naught T naught. And the blue line, when it gets over there, is going to have to pass through that point. So this is called the S coordinate curve. And likewise, if I drew a point where S was equal to S naught, and I looked at what happened to the T variable as I sweep through the domain, I get a different curve. So this is called the T coordinate curve. And the idea is this actually gets us what looks like a little coordinate system at every point in the surface that we've parametrized. And those curves are going to have derivatives, which means they're going to have tangent vectors, which means I'm going to be able to use this idea to cook up a tangent plane for every point inside of a surface, assuming that my surface is nice enough. So the idea is this is going to give us this is the basis. I should say foundation here, since I just talked to linear algebra students. This is the foundation of tangent structure in a parametrized surface. Okay, so this is a good place to pause for a second. Is this okay? Is anybody lost in what's going on here? The idea is we have a map that takes a rectangle or any other set in R2 and turns it into some kind of sheet in R3. So it's a twisty, bendy thing. And what I'm saying is if you look at straight lines in the domain and you look at where they go, they sort of give me a coordinate system on the surface. Like the lines on a globe, for example. You can think about this as giving you a set of latitude and longitude lines on the surface. It gives you a way of locating where you're at, and it tells you, it gives you something you can take derivatives of that would tell you the slope of the surface at any particular point. Okay so far? All 14 of you that are in here? Okay. Okay, so I guess I'll give you another concrete example of one of my favorite objects. This is a thing that I study all the time in my research. Don't worry, it's not so hard that you can't understand what's happening. If you look at this particular map, so you take x of s of t and you define it to be, well, the x coordinate of your parameterization is given by a plus b cosine of t times the cosine of s, and y of s of t is equal to a plus b times the cosine of t times the sine of s, and you let z of s and t be equal to b times the sine of t. Is that right? T, T, S, 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 T. And you let your domain here be t variables running from 0 to 2 pi. Sorry, s from 0 to 2 pi and t from 0 to 2 pi. But this thing is the delightfully difficult to draw torus. So it's not hard to show. You can look this up in Kali if you want a better picture than I'm going to be able to draw. So Kali does a pretty good description about why this is the torus. What this looks like is this. So there's sort of a donut shape here where it comes around the front. And I can show you how the map works by showing you what happens to the lines. So you start with this rectangle. It's 2 pi, 2 pi. This is your original domain D. And X is going to take that and turn it into this. Lines that go in this direction in your domain turn into lines that run around the torus this way. So torus is kind of a hollow donut. So every line here that you draw gets you a different line in the torus. On the other hand, if you draw lines this way with this map, then you get circles that wrap around like this. So each line that you draw here gets you a circle that wraps around the torus this way. So one direction parameterizes to sort of like like large round, like the sort of, I don't know what to call the dimensions of a donut, right? Like sort of the circular part that makes it into a like sort of a big ring. And then in the other direction, you get the circles that go around and wrap through the hole. Okay. And the idea that, so that, again, this map is in Kali. It's pretty easy to understand using the standard sort of a squared plus b squared equals r squared, or sorry, x squared plus y squared equals r squared circle equations. But the nice thing about like working with something like this, if you were working with the torus, is if only you could figure out, say right here, if you could figure out the tangent vector of the blue curve, and you could figure out the tangent vector of the pink curve, then you could use that to form a tangent plane, or if you like, you could use it to form a normal vector n. And that's the goal. If we could figure out ways to compute tangent vectors of those curves, that's going to give us a way of computing a normal vector to the surface. And normal vectors to surfaces are awesome because they encode both direction and area information. So that's why we're using these sort of parameterized things. So we're building up to defining scalar and vector integrals against surfaces. And that's why we're doing it with this approach. Okay, so before I go on to my definitions of TS and TT, are there questions about this? I know this is kind of like more abstract than the stuff that we've been doing. Okay, so I'm just going to reiterate. The idea is if I could differentiate the coordinate curves, I could get tangent vectors, which would mean that I could get a tangent plane, which would mean that I could get a normal vector. And so that's the next thing we're going to do, is talk about how to actually compute that. So here's the next definition. If X is C1, which remember means continuously differentiable, oh yeah, I should say C1 at every point in D. And S is equal to X of D. Then we call S a differentiable surface. Okay. So if X is a continuously differentiable map, then that means the surface carries some notion of differentiability. That means we can define TS with a tangent vector in the S direction at the point S naught T naught. The obvious way to set this definition up is calculate the S derivative of X. So here we're going to assume that X is equal to X of ST, Y of ST, Z of ST. And then we're going to set this up to be dx ds at S naught T naught in the I direction, and dy ds times S naught T naught in the J direction, dz ds at S naught T naught in the K direction. Up here, you can imagine that that corresponds to a derivative of this pink curve. So at this point right here, this vector I would call TS. It's the tangent vector that is tangent to a curve in one of these pink lines, one of these coordinate curves in the pink direction. And likewise, we can define a tangent vector in the T direction by just taking T derivatives. And the idea is, again, here what we're doing is we're capturing what happens as if we fix S and we let T move. This is kind of what we're capturing with these partial derivatives. And if we go back up here, that would be like saying, oh, draw yourself, not that color. Draw yourself a coordinate curve in this direction and calculate what this vector was. And we'll call that vector TT. So it's the tangent vector associated with the T coordinate curve. Okay, well, the nice thing about two tangent vectors is they form a tangent plane. And that means I can form a normal vector by the obvious way. So we define color. So now we can define what's called the standard normal vector. At x of s naught t naught by n of st is equal to, sorry, I should say x of st is equal to ts at st cross tt of st. That picture looks like this. That point right there, we think of as being x of s and t. I have a curve that cuts through like this and a tangent vector associated with it called ts. I have a curve that cuts through like this and a vector associated with it called tt. And if I cross those vectors, I'm going to get a vector poking out this way called n. This right here is the core of basically all contemporary differential geometry, which is the idea that the surface, all the behavior of the surface lives in the behavior of this normal vector. So the normal vector and the behavior of the normal vector captures deep information about everything else about the surface, which will become clear in a second. So I guess if I was going to be completely appropriate here, I should be putting hats on all these guys because they're vectors. There, now I have it. Okay, so we have one last thing that we need to make sure it doesn't happen if we're going to study these things with calculus, which is I can't ever have the normal vector go away. Like the normal vector always has to be present. If the normal vector is not there, it's almost like the surface has disappeared in some sense, right? That if there's no direction, the surface has no direction. So we're going to make the additional demand that a parametrized surface is smooth if n of st is not the zero vector for any st in the domain. The disk, I'm sorry. So if the normal vector never disappears, we call it a smooth surface. That's even nicer than differentiable. So you can be differentiable without being smooth. Smooth is pretty nice. Okay, now this is the sort of like the domain of like all the beautiful theorems, is differentiable surfaces. And in fact, for those of you that have pretenses of going on, not pretenses, ambitions is what I should say, but not pretenses. If you have ambitions to go on higher level math, this points the way to what's called differential geometry, if you're interested. There's a whole notion of the study of surfaces by way of their associated vectors called differential geometry. It's actually the basis of relativity in physics. Okay, so our very first application, we spent all this time setting up this machinery. And the very first thing we're going to do with it is we're going to set up a different way of computing the surface area of a surface. If you remember back to your Calculus 3 class, this is one of the ugliest things you do in Calculus 3, because every surface you can do surface area of is a surface of rotation, and the integral is awful. I mean, it's not much better here, but at least it's not got a square roots running around all over the place. So we're going to use this setup to define surface area. surface area of a surface. And we're going to make the following observation. If I have some domain here, and X takes that domain and it maps it up into a surface bending through space. And I want to cut that surface up into pieces that I can add the surface area up. That's kind of hard, but we have an approach that we can take here that is founded on starting with little rectangles over here in the domain D. So if I take a little rectangle over here, say delta S by delta T, and I look at how delta S by delta T gets carried over into the surface, well, what's going to happen over here, say we got some anchor point. So you can imagine that what happens over here is that this ends up carving out some kind of weird, kind of almost rectangular shape. So the interior of this kind of bends in the surface over here. But the idea is that that shape over there is almost equal to the tangent plane that's described by the tangent vectors. So I can think about this shape over here, which I call ds. I should be careful. ds now, d capital S, not d lowercase s anymore. That rectangle over there is basically approximately equal to this shape, tt ts. And if you think about for a second, the geometry of a parallelogram that is swept out by two vectors, one of the fundamental facts about parallelograms and their associated and cross products. Actually, I'm curious, does anybody remember what the relationship is between parallelograms and cross products?
The norm gives the area.
The norm gives the area. And so we have two different things that this is doing. So the norm of TT cross TS is about equal. I mean, it's going to be about equal to this T, or it's not about equal to DS. I have to take this and I have to multiply by the DTS and DT as well. But the idea here is, yeah, this is equal to the area of a parallelogram. But it's also equal to the length of the normal vector, because we defined n of st to be equal to that cross product. So we have two different ways of thinking about this. And so on the basis of this observation, that what x does to this little rectangle is it carries it over here into the surface. And so that means if we cut this up, we would be cutting this up into pieces that look like that. As we define the quantity ds to be equal to the length of tt cross, doesn't matter what direction I do it, but I guess I should be consistent here. TS cross TT DS DT. This is like picking up the distortion factor. If you start with a little tiny unit, delta S delta T, and you want to keep track of what the area it gets mapped to, well, the distortion factor is granted by this parallelogram. And then you multiply that by this, the original dimension is DS DT. So this is our notion of big DS. And with that notion, we get the definition of the surface area. So the surface area of x of d is defined to be equal to the double integral over d, the length of ts cross tt, ds dt. And we think about this as the area of the little pair, the area of the image of delta s, the rectangle given by delta s delta t. And if you like that instead, you could write this. This is the length of n of st ds dt. And if you want to completely get rid of the idea that there's an n running around at all, you could just do this. It's double integral over d of ds. So in the same way that when we encoded arc length, one of the ways of thinking about arc length was the integral of ds. This is sort of the same kind of idea. And this is a big deal, right? Because there's no function here, right? The function has disappeared. There is no function here. But yeah, I guess I need to put x here to emphasize that like there's still a surface that's being parametrized. But the idea is that there's no function because the normal vector is carrying all of the information of the surface, which is a really weird fact, right? that somehow the normal vector carries all the information about a surface, which is weird and cool, because the normal vector doesn't just tell you what direction the surface is going, it tells you how it's distorting the little, the little areas that you put in. It tells you what the expansion factor is there as well. So this kind of gives you a way, like one way of thinking about what this does is it gives you a way of sort of taking a bunch of little rectangles, and then I guess the analogy I always use here is it's like you're getting something that looks like an alligator skin out the other side. It's a bunch of flat plates that fit together that kind of like sweep out the surface. And the smaller the rectangles you use, the finer the scales are going to be. Okay. Questions about that? This is, again, I know this, like I said, I know this is abstract, but this is what this math starts looking like. And if Calculus 4 and 304 were designed correctly, then we would have been doing a lot more of this earlier in the class. If I had my druthers. Any questions about this? Okay, so I guess the next thing we could do in the sort of 5 or 6 minutes we have left here is we can talk a little bit about, does it matter how I choose to parameterize a surface? Should it matter how I choose to parameterize a surface? If I have some surface that's floating around in space, like, I don't know, say I've got a half sphere. Here's some S. Just there's a surface. To find a parameterization for the sphere would be to find a domain D and a function X that takes D into R3 so that X of D was equal to S. Well, what if I found 2 of them? What if I find a different one? What if I said, oh, well, I could find a different domain, D prime, and a different function, X prime, that takes D prime into R3, but I get the same surface out the other side. Suppose I do a different computation, but I get the same surface, so that X prime of D is also equal to S. So the question then is, does it matter in any of the computations I do, should it matter how I parameterize the surface? I mean, like, I suppose I computed the surface area of this. Actually, there's a quick challenge. What is the surface area of a sphere? That's not supposed to be a challenge. You should probably have that in your head somewhere. Let me know. Indeed, 4 pi r squared. Okay, cool. So a half sphere is going to have a surface area of 2 pi r squared, right? Does that change based on the way I set the sphere up? Well, no, it shouldn't, right? I mean, surface area is a surface area. The surface area of this is 2 pi r squared. It should not matter what function I use to build it. So, like, there's a lot of different ways to do this. I could use a polar version to build this thing. I could use a spherical version to do this. I could use a functional version to cook this thing up. There's a lot of different parameterizations of this thing I could use. It shouldn't matter. Surface area shouldn't depend on how I've parameterized the surface. And so one thing that we hope when we're doing these things is that parameterizations don't change the computations we're doing. So there's a big question here that we're going to have to deal with when we start talking about line integrals, is that it shouldn't be the case that different parameterizations produce different computations. And if the math has been set up correctly, that absolutely shouldn't be the case, right? I mean, and you might think that, like, it could. There's no reason to believe it couldn't. I mean, why should the normal vectors be the same? If I have a different X, I'm going to get different coordinate curves. And if the coordinate curves are different, then the tangent lines are different. And if the tangent lines are different, then the normal vectors are different. So what on earth is going on with that? How could we have two different parameterizations of the same thing with different normal vectors? Where does that get accounted for? That's something to think about. Like, where does that get accounted for? The fact that, these aren't unique. They're highly non-unique. Parameterizations are highly non-unique. Even with this half sphere right here, one version of the half sphere is given by the same parameterization we had earlier. Like when I did the sphere like this, right? Where did I do it? When I did the sphere right here, there's no reason I had to use the entire interval from 0 to 2 pi to do this. I could have used the interval from 0 to pi to get a half sphere instead. But I could also think about it as z is equal to f of x and y, which gives a different parametrization of the sphere. Very different parametrization. One in spherical coordinates, one in Euclidean coordinates. So we need to make sure that when we're setting our machinery up here, that we're careful to make sure that different parameterizations of the same surface lead to the same computation. This is the same as being path independent when we were talking about those. It's not quite the same as path independence, but the idea is that parameterization should not affect the computations, and that's going to have to be dealt with. And actually, that leads me to a question, which is, how many of you guys have? Is there anybody here who's actually seen Stokes theorem before? Because the calculus 4 classes are supposed to get to it, and they hardly ever do. Has anybody actually seen Stokes theorem? Have you done anything with it? Have you seen like the Stokes trick, like basically the reason the Stokes theorem exists? Oh man, okay. So I am very eager to show you guys the Stokes trick, because it's one of the cheesiest moves that exists in this in calculus. It's amazing. And I'm going to tell you that it's basically, all right, so I've got 2 minutes. I'm going to tell you something delightful that we're going to get to see. So in the next class, so the next time, what we're going to do is we're going to define line and vector integrals. Following the same path, following the same path we did with the path integrals, right? We came up with the notion of a parametrized path, and then we set up line integrals and vector integrals. We did the same thing with surfaces. And it's going to turn out to be the case that we get to play this amusing trick where I define some surface like this. And there's a theorem that says, oh, well, a certain kind of integral on a surface like this is equal to a different kind of integral just on the boundary of that surface. But then that's equal to any other surface that you can plug into the same boundary. So there's this trick that oftentimes gets used in higher math and physics where you say, oh man, this really sucks to compute because I don't want to work with this paraboloid. So then you just throw the paraboloid away and put the disk in instead, which is beautiful. So if you have no idea what I'm talking about, I promise I'm going to, even if I'm just amusing myself when we get to this, we're going to talk about something called the Stokes trick, which is related to vector surface integrals. And ultimately, the point of what we're doing right now is to talk about flux and divergence in R3, which is why you might expect that this is sort of related deeply to the core ideas of mathematical physics. All right, guys. Well, thanks for hanging out with me today. And if you want to see the more detailed version of this, or an alternate take on it, you can look at my other video. I'll have these posted this afternoon. And yeah, if there's questions about stuff, you guys can send them to me. I'll make a post about the homework. And then everything else I can get, I will get done as fast as I absolutely can. And yeah.
Professor?
What's up, Lamb?
When's your next office hour?
I'm gonna hold office hours on, I'm gonna try to hold them on, what is a good time to do it? I'm gonna have a long office hour on Friday. It's like, so for like 2 or 3 hours of office hours on Friday, and I'm gonna hold them on Saturday, and I'm gonna try to hold them on Monday morning as well.
Is there like a review session?
There's not a review material. There's not a review. You mean, is there a review day?
Yeah, like reviewing what's gonna be on the final.
Yeah, so that basically, because of the way that the course content is compressed, I'm going to make a post about that. The basic idea is that like what's going to be on the final is mostly exam 1 and exam 2 with a couple of questions from this final section about Green's theorem and Stokes theorem. These are sort of hard to test, but yeah, there'll be so we'll either talk about that on Thursday in class, or we will talk about it or I'll have a video posted and we'll just do like an actual review session like on Friday or on Monday before the exam.
The other question I have is within the last 2 weeks content, is everything online currently?